I would love to make these insertion operations a lot more tangible. So what we're going to do is I'm going to show you pseudocode for these operations. And again, you know, my pseudocode is almost Python code. It just takes a few shortcuts here and there and tries to make things a little more clear. So let's say we have our red-black tree insertion operation. We have our tree, and this is just a pointer to the root node. And we're going to insert a newly created node. Let's just say the node's already been created out elsewhere. First thing to do is to search for a position of the new node. So let's say we want to insert 34. How do we do that? Well, we know we're eventually going to sort of make our way. So 34 is to the right of 20, to the right of 25, to the right of 30, and to the left of 35. So we know eventually we want our new node to end up here. Let's see what that actually looks like in code. I'm going to set parent equal to none. Current node is equal to tree.root. And we're going to say, while current node does not equal none, we're going to keep running our procedure here, our loop. We'll say parent equals current node. Well, current node starts out here at the root. So let me just say we're inserting a 34. And let me just put a marker on where current node is. So current node is here, and parent node is here. And parent node will just sort of follow current node around. Next, we say if new node.key is less than current node.key, which it's not. Well, in that case, we would have gone left, but here we're going to go right. So we'll set current node equal to current node.right. So current node is now 25. And we go up to the top of the loop. Is current node none? No, it's the node 25, and we're going to again do the if check. Well, first we actually moved parent down to here. So current node's there, no longer there, parent's no longer there. And we know that 34 is greater than 25, so we're going to move current node down to here. And then at the top of the loop again, current node is still not none, so the parent node follows it. And again, we're going to go to the right, so current node becomes 35. And then parent node is going to follow it down. And then finally, we'll set current node equal to current node.left because of this code. Because new node key 34 is less than current node.key, which is 35. So we say current node equals current node.left, which puts current node down here, which is a null value, or none in the case of my pseudocode. So current node's no longer there, but parent is still there. So we're going to set the new node's parent equal to whatever the parent is that we got from that loop, which is correct. Okay, so we've searched for the position, and we know our new node 34 is going to end up being here, and we've actually already wired this part up. We've wired this part up. The node has a pointer back to its parent. Now we have to figure out, well, is the current node to the left or to the right of the current node? Well, if parent ended up being none, that's the case when we would have been inserting as the root. So we would have just said tree.root is equal to new node. Otherwise, if the new node's key is less than the parent key, which it is in this case, we say parent.left is equal to new node. So now we've got that left pointer on there. Otherwise, it would have been to the right. All right, so now we need to initialize our new node. So the first thing we're going to do is set its left and right equal to none, and we're going to color it red. That's always our default color. So we have this pointer, and we have a pointer going back. We have null and null. And that's all we have to do for the inserting part, but now we have to fix colors. So if we jump to this procedure, we have 34. We have to fix our color. So we say we inserted our new node, so this is our 34 node here. And we say, well, node.parent.color is equal to red. Well, that's true, that 35 is red. Remember, if it was a black node, we would be done. From our plain English explanation of it before, we would have just been done. But in this case, we have to key off of the aunt node. So if the aunt node, which is, again, you have to go to the parent, and then you have to go to the parent's parent, and then you go to the left. And if that equals, we're going to set aunt node equal to that node. Oh, I'm sorry, I've got this a little bit backwards. Let me clear this off. We've inserted 34, it's here. We're going to say if parent node, so we're going to say this node here, the parent, is equal to our node's parent dot left, which it's not equal to. That would be if our aunt node was to the right, which it's not. Our aunt node is to the left of its grandparent. So under those circumstances, we would have gone down this path. But we're not. So let's do the else branch here. So if our node, 34, and now we're going to look at this one as the aunt's node. So aunt is equal to the parent's left node. And if that's a red node, what are we going to do? Exactly what we had before, which is we're going to color the parent node to be a black node. So we're going to recolor this one to be a black node. And we're going to color the aunt to be a black node, which is this one. And we're going to color the node.parent.parent to be red. So that's the grandparent. Color this one red. And then we say node is equal to node.parent.parent. So we come back up here to the top of the while loop and act as if the 30 was the node that we had just inserted. So we say, is the node parent equal to red? And it is, which means we have to keep going through this loop. Now, there's another case here, which is what do we do if the aunt's node is a red node? So the previous case was when a black node. The previous case was when the aunt was a red node, and now we've got the else case here, where the aunt is a black node. And we know under those circumstances we have a little bit more work to do. So we're going to say node is equal to node.parent, and we're going to do a right rotation around that node. And then when we come back from that right rotation, we do the coloring that we had mentioned before, and then a left rotation. So this is where those right and left rotations are going to come into play. Because under those circumstances, if this was a black node, we would have had a right-left insertion, which means we do a right followed by a left rotation. All right, at the very end of this while loop, we would have done a bunch of recoloring, and all we have to do is make sure at the very end that we remember to set the root back to being the color black. And that's one of our red-black tree invariants. Okay, so hopefully that makes at least some sense. If it doesn't, you'll have a chance to look at that code and the exercise and work through it and have more time for it. And if you have any questions on that code, please feel free to come by office hours and ask more about it. But before I start the next video, I want to and have you work and send you off to work on the exercise. I want to talk about one more example here. So first, my question is this a valid binary search tree? And the answer to that is no, because we have 25 at the root, and that means everything to the left of it has to be less than it, but we've got this 28 here. So that 28 really should have been inserted to the right of the root. Okay, so now if I color this tree, is this a valid red-black tree? And the answer here again is going to be no. I have one black node on this root to null path, and I have two on some of the others. How about if I insert a black node here, and now I have a valid red-black tree? Next question, is this the only valid coloring of this red-black tree? Well, when looking at valid colorings, you want to see, do I have a black node where I could push the color black down? Because if I take, for example, this color here and push it down, I can still make sure that I have two black nodes on every path. So this one, this one, this one, and that one. So, for example, I could push that color down, and now this is another coloring. There's no particular reason you'd want to do this. I just want to point out that red-black tree colorings are not unique. So another question would be can I do it also for this node? Well, the problem here is if I push the color down, I now have an invalid red-black tree because I have two red nodes in a row. So it's not that you can always push that color down. All right, so now is the great time to start working on exercise question 3, and then when you come back, we'll step through it together.